I will be describing how to use the Fourier transform infrared spectrophotometer and how it works. Here are a couple facts about FTI Spectrophotometer. The whole spectrum is obtained at once. It is a mathematical algorithm used to convert the information obtained by the detector into a conventional spectrum. Fast computers scan the entire spectrum multiple times in a very short period, and then they average the total spectrum. This increases the signal-to-noise ratio. Here are the steps of how the instrument works. The light beam strikes a beam splitter, causing half of the light to be directed onto the fixed mirror and the other half onto the moving mirror. This is the beam splitter. Half of it goes this way, and then half of it goes to the fixed mirror. Then the beams combine to form constructive and destructive interferences depending on the condition of the moving mirror relative to the fixed mirror. When both signals are the same distance from the beam splitter, the two reflective beams pass through the exact same path length and are completely in phase. The signal intensity is at its maximum. Next, the modulated beam that is reflected from the mirrors passes through the sample where selective absorption takes place. So here, after it goes through the mirrors, it comes back into the sample. After the beam passes through the sample, it continues onto the detector, which translates the beam into electrical signal. So that's pretty much how the FTIR instrument works. You need to make sure to use caution because the FTIR instrument includes a laser, and when you're looking inside the instrument and the cover is off, it can become very hot.
This is the equipment that we're using. It's a FTIR spectrophotometer. Okay, we're going to start off by running a background spectra, and we're going to use these two potassium bromide plates. Hey, cameraman! Alright, so as you see, these are the first couple drops. This should be the most pure of the distillate, and that should be almost all cycle that. Okay, we'll go ahead and run the background now. Click collect, background. We'll call it BG for background, and let it do its thing. Next, we'll run our first sample, heptaldehyde. One drop, and then place the second plate on top of it. Okay, we'll run it just like before. Go to collect, sample. We'll call this SA1 for sample 1.
Yeah, but yeah. Just like that. So I'm just gonna go back.
I really sense it.
Interpreting IR spectra results.
When looking at an IR spectrograph, the most important wavelength region to look at is between 4,000 and 1,500. In this region, any peaks noted will correspond with specific functional groups. The region, known as the fingerprint region, which ranges from 1,500 to 400, should be avoided. First, focus on the peaks of major functional groups. If the peaks are flat on the bottom, this may mean the sample is too concentrated. Conversely, if the peaks are too weak, the sample concentration may be too low. If water is present in the sample, it may show a peak at 3,200 to 3,600, which could be misconstrued as in alcohol. Air can also cause a doublet peak at 2360 wavelength region. So, for some examples on interpreting graphs, we have the following. Example, alcohols will present a broad, intense peak at around 3,300. This is where the OH bond stretching absorption takes place. In our second example, aldehydes represent their C double bond to oxygen stretch at about 1710. In addition, two stretch bands at 2720 and 2820 for the carbon-hydrogen bond. In our last example, ketones have a peak at about 1718 that is strong and sharp. This peak represents the carbon-oxygen double bond stretch.